In April 2025, a team of scientists pointed the most powerful telescope ever built at a faint smudge of light in the sky. What they found didn't just break the record for the farthest object ever seen by human eyes. It might break cosmology itself. This is the story of MOM Z14. And once you understand what it is, you will never look at the night sky the same way again. Light moves at 186,000 miles per second. That is the absolute speed limit of the universe. Nothing can go faster. And yet the photons that JWST just caught from MOM Z14 have been traveling for 13.5 billion years. They left their source when the universe was just 280 million years old. To put that number into something your brain can actually grip, imagine compressing all of cosmic history into a single calendar year. The Big Bang is January 1st at midnight. You and I, modern humans, show up in the last 10 minutes of December 31st. The dinosaurs don't arrive until Christmas Day. And MOM Z14? It existed on January 7th, 7 days into the universe. We just took a photograph of it. If that doesn't make your brain short-circuit, stay with me, because it gets stranger. Before we go further, if you're new here and you love having your mind rearranged by the universe on a regular basis, hit subscribe. It's free, it takes 1 second, and honestly, the universe deserves a witness. Now let's get into it. The James Webb Space Telescope launched in December 2021 and began science operations in 2022. It was built for exactly this kind of hunting. Its 6.5-meter gold-plated mirror, its infrared sensors, its ability to peer through the cosmic fog of the early universe. But even by JWST standards, MOM Z14 was a shock. A team at MIT's Kavli Institute was combing through existing JWST data when they spotted something suspicious, an object that appeared in infrared wavelengths but vanished completely at shorter wavelengths. That dropout pattern is a signature. It means the light has been stretched so dramatically by the expansion of space that everything below a certain wavelength has been redshifted entirely out of the visible range. They pointed JWST directly at it. They used the near-spec spectrograph to split the light into its individual wavelengths like a cosmic prism, and the number that came back stopped them cold. Redshift equals 14.44. For context, the previous record holder, a galaxy called JWST, had a redshift of 14.18, placing it at 290 million years after the Big Bang. MOM Z14 beats that. Its light left it at just 280 million years post-Big Bang. We are looking at something from a time when the universe was roughly 2% of its current age. The scientists didn't name it MOM Z14 as a joke. They called it the Mother of Miracles, because that is exactly what they said it was, a cosmic miracle. But here's where it stops being just a record and starts being a problem. MOM Z14 is small, about 240 light-years across. Our Milky Way is roughly 100,000 light-years wide, so we're talking about something 400 times smaller than our own galaxy. In the early universe, that makes sense. Structures hadn't had time to merge and grow yet. But here's what doesn't make sense. MOM Z14 is extraordinarily bright, blazingly, impossibly luminous for its mass and size, far brighter than every model of early galaxy formation predicts it should be. And our models aren't casual guesses. They're built on decades of observation, mathematics, and simulation. They've been tested against thousands of galaxies, and MOM Z14 is laughing at them. The question that keeps astronomers up at night is simple. How is it this bright this early? But wait, there's more. When the team analyzed MOM Z14's spectrum, they found a chemical fingerprint that made them go very quiet, a high ratio of nitrogen relative to carbon. That specific ratio is unusual in galaxies this young, but it's not unprecedented. We see those exact same ratios in one particular type of structure, globular clusters. Now, Globular clusters are some of the oldest stellar objects in the known universe. Dense, spherical collections of hundreds of thousands of stars orbiting the cores of galaxies like ancient satellites. We always assumed they formed over the first few billion years of cosmic history. We had a whole timeline for it, a comfortable, ordered timeline. And MOM Z14 just torched it. If this galaxy already has globular cluster chemical signatures at just 280 million years after the Big Bang, that means globular cluster formation didn't take billions of years to begin. It may have started almost immediately after the universe first became transparent. That rewrites the timeline, not tweaks it, rewrites it. And here's the thing that should genuinely unsettle you. MOM Z14 is not an anomaly. Since JWST began science operations in 2022, it has found galaxy after galaxy in the early universe that is too bright, too massive, and too chemically complex for its age. Not one or two outliers. A pattern. A growing, undeniable pattern of galaxies that should not exist the way they do. This early, at this scale, our models of cosmic structure formation keep getting surprised. And in science, when your models keep getting surprised by the same category of observation, that's not bad luck. That means something fundamental is missing from your understanding. What is missing? Scientists have several ideas, and none of them are small. One possibility is that dark matter played a far more aggressive role in seeding early galaxy formation than we thought. Dark matter makes up roughly 27% of the total energy content of the universe. We can't see it directly, but we know it's there because of how it gravitationally pulls on the matter we can see. If dark matter clumped together and collapsed into dense halos far earlier and more efficiently than our models allow, it could have provided the gravitational scaffolding for galaxies like MOM Z14 to build themselves at an almost impossible speed. Another possibility is that the first generation of stars, what cosmologists call population 3 stars, were far more massive and far more energetically violent than we imagined. Stars so enormous they would have burned through their fuel in a fraction of the time and exploded as supernovae with such force that they seeded the surrounding gas with heavy elements almost instantly. That could explain the chemical complexity we see in MOM Z14 at an age when the universe should still be chemically primitive. But there's a third possibility that is significantly more destabilizing, and it connects to something else entirely. Recent research has surfaced a pattern that shouldn't exist in a universe built on randomness. When astronomers map large-scale galaxy distributions across the sky and analyze their rotation, they find something troubling. A statistically significant majority of galaxies appear to be rotating in the same direction. In a truly random universe with no preferred axis, no built-in orientation, galaxy spin should be roughly evenly split, left and right, clockwise and counterclockwise, a coin flip at cosmic scale. But that's not what we're seeing. There appears to be a preferred direction, a cosmic axis, an asymmetry baked into the large-scale structure of the universe itself. This is sometimes called cosmic anisotropy, and it challenges one of the most foundational assumptions in all of cosmology, the cosmological principle, which states that on large enough scales, the universe looks the same in every direction. No preferred position, no preferred axis, pure statistical uniformity. If that principle is wrong, or even just approximate rather than exact, then every model built on it needs to be revisited. So why might the universe have a preferred spin direction? Here is where things get genuinely philosophically uncomfortable. One of the theories that has gained serious traction among theoretical physicists is called black hole cosmology, sometimes called Schwarzschild cosmology. And it proposes something that sounds like science fiction, but is grounded in real mathematics. It suggests that our entire observable universe might be the interior of a black hole that formed inside a larger parent universe. Think about what a black hole actually is. Matter collapsing under gravity so intensely that it creates an event horizon, a boundary beyond which nothing can escape. Beyond that horizon, the normal rules of space and time break down. Now think about the Big Bang. The universe beginning as a singularity, a point of near-infinite density, near-infinite heat, then expanding outward. Sound familiar? That is structurally identical to the description of matter collapsing into a black hole. The singularity at the center of a black hole and the singularity at the origin of the Big Bang are mathematically described by the same equations. And the question that naturally follows is whether those two things might actually be the same kind of event, just viewed from different sides of an event horizon. If our universe is the interior of a black hole, then the Big Bang wasn't an explosion in empty space. It was the moment a collapsing mass of matter in a parent universe crossed its own event horizon and spawned a new universe inside. And by extension, every black hole in our universe could be doing the same thing right now, each one potentially seeding its own baby universe on the other side of its event horizon, with its own physical constants, its own laws, its own expanding space-time. This idea has a name: cosmological natural selection, proposed by physicist Lee Smolin, and it has an interesting implication for the fine-tuning problem. The question of why the fundamental constants of nature seem precisely calibrated for the existence of complex structures, chemistry, and life. If universes reproduce through black holes, and if universes with physical constants that produce more black holes create more offspring universes, then over many generations, the constants that produce complexity in black holes would be naturally selected for. The universe would be fine-tuned, not by design, but by something analogous to evolution. Now, none of this is proven. These are theoretical frameworks. But they are serious theoretical frameworks discussed in peer-reviewed literature, motivated by real observational puzzles. And MOM Z14 is exactly the kind of observation that makes physicists take them more seriously. Here is what I want you to sit with for a moment. We built the telescope. Humans, a species that has existed for maybe 300,000 years on a planet that has existed for 4.5 billion years, in a galaxy that has existed for 13 billion years, in a universe that is 13.8 billion years old. We built a telescope, launched it 1,000,000 miles from Earth, and pointed it at a patch of sky, and we caught light that has been traveling since the universe was 280 million years old. We didn't just detect that light, we analyzed it. We extracted its chemical composition. We measured its redshift to 4 decimal places. We identified its size, its luminosity, its age, its place in cosmic history with precision. And what that light told us is that everything we thought we knew about how the early universe works is incomplete. That there are galaxies out there that shouldn't be as bright as they are. That globular clusters formed faster than we thought. That the universe might have a preferred axis. That our entire observable reality might be nested inside something larger. That the map is not the territory, and the territory is stranger than the map ever suggested. The record MOM Z14 holds will not last. JWST is still looking. There are almost certainly galaxies out there with redshifts of 15, 16, maybe higher. Galaxies whose light left them even closer to the Big Bang, even deeper in the dark ages of the cosmos. And every one of them is another data point. Another constraint on our models, another chance to find whatever it is we are missing. Science doesn't break when it finds things it can't explain. Science is built for exactly this moment. The anomaly is not a failure. The anomaly is the invitation. So here's my question for you, and I genuinely want to know what you think. If it turns out that our universe really is inside a black hole in some larger parent universe, does that change anything for you? Does the meaning of existence shift if there's something outside the universe we can never reach or observe? Drop your answer in the comments. Seriously, I read them, and the best responses tend to start arguments that go on for days, which I consider a success. If this video made you think, if it pulled the floor out from under you even slightly, the single best thing you can do is share it with one person. Not for me, for them. Because these ideas deserve to be in more conversations. And if you want to be here when the next distance record falls, which it will, subscribe and hit the bell. We're going to be covering every major JWST discovery as it happens. And if this channel has ever genuinely rewired how you see the universe, the super thanks button exists, and every single one of them goes directly into making these videos better. You're not tipping a creator. You're funding the kind of content that makes people stop scrolling and actually think. That matters. Thank you for being here. And as always, see you at the edge of everything.